Good afternoon to everyone. I am Nadine Al-Kosafi, Marketing Product Manager of Forge, Cold Form, and SIMHEAT.
Good afternoon. My name is Max Pinago. I'm in charge of technical aspect for Forge, Cold Form, and SIMHEAT as a technical product manager.
It is our pleasure to welcome you today to our webinar dedicated to the novelties in heat treatment simulations. Now the camera will be turned off and it will be back during our conclusions. Before starting, just a few words about the GoToWebinar platform and how to operate the control panel. You can use the orange arrow to minimize the control panel to the right. By default, the microphone will be turned off for all participants during the presentation. At any time during the presentation, feel free to type your question in the dedicated area, and we will answer all these questions at the end of this webinar. During this talk, I would like to start by a small introduction about our company TRANSVALOR and the software solution we offer. After having reviewed the global scope of our solutions, we will focus on several novelties in heat treatment applications. The third part of this webinar is dedicated to the heat treatment case studies. After the conclusion, we will be happy to answer your questions. Who we are, what we do, and how can our solutions help you in your daily work. TRANSVALOR is a world-leading software editor providing cutting-edge solutions for virtual manufacturing. The company has been founded since 37 years ago. TRANSVALOR contributes to the innovation of the today and tomorrow. For example, in the automotive industry, TRANSVALOR solutions allow cars worldwide to run securely. We supply the manufacturing industry with process simulation software giving keys for rational engineering decision-making. We provide added value engineering consultancy and services to tackle new technical challenges that you might encounter. We work in very close partnership with SIMHEAT Paritech Research Laboratory with more than 120 scientists, allowing research results to be integrated constantly in our products. Our products are used worldwide in different industries, like energy, aerospace, and the automotive industry, of course, and in heavy industry as well as in research institutes. For all our customers, we are committed to provide first-class simulation software and services. For those who don't know TRANSVALOR, we offer different products to help you master your manufacturing processes and increase parts quality and productivity. Our solutions can be used at any step of your production, from the foundry to the forming until the fatigue calculation, now available with ZZ software. Among these solutions, two of them allow you to simulate the heat treatment processes, Forge and SIMHEAT. SIMHEAT is a known product for only heat treatment processes, and this product is a module of Forge software. All new features are implemented in both software. Now we will dive into the main topic which you are interested in, the heat treatment processes. Let's start with the global scope of our capabilities to simulate heat treatments. Today, the heat treatment operations are mandatory to answer your part mechanical performances. Heat treatment operations take place after metal forming or machining. As you can see, we address all the heat treatment processes. Thanks to the numerical simulation, a complete management of incoming and outgoing material can be achieved with SIMHEAT. You can predict and analyze several results such as temperature evolution, phase transformation, hardness, distortion, residual stress, carbon and nitrogen concentration. It is possible to generate a report of the whole production process with different graphs. With SIMHEAT, you can determine the data of the incoming which has to be processed, and you can prepare a chart of your heat treatment cycle. The software allows to define a complete heat treatment cycle by controlling the different heat treatment operations, by controlling the heating, the cooling rates, and the quenching. In our software, you will find a large material database for steels, aluminium, and titanium alloys, as well as a rich quenching database. If your material file doesn't exist in the database, it is possible to import it from GMAT Pro to our software. The graphical user interface includes several dedicated process templates to make your data setup easier, as well as several tutorials to learn how to use the software. Your highest priority is to obtain the parts that respect the customer-specific mechanical and microstructure properties. To achieve your goal, we provide you accurate predictive simulations. We improve continuously our innovative solutions through novelties. First novelty is the oxide scale growth prediction. As you know, the hot metal reacts with the air, and an oxide layer can be observed on the surface. Depending on the nature of the part, the oxide scale thickness can have some impact on the heating and the time cooling, as well as on the forming operations. To achieve more realistic results, we are now able to model the oxide scale growth. Then first, we will start with the heating operation. For the longest time, heat treatment was considered as a black box. We know what goes in and we know what comes out, but what happens in between is a complete mystery. In this example provided by Framatome, we heat a hollow shell made of C55 to 1100 degrees Celsius. The question is, what happens inside the furnace? How the microstructure evolves? And how long do I need to get a homogeneous temperature? Here we see the temperature distribution during heating. Then we can see that at this sensor, we have the temperature distribution. In these videos, we can follow the different phases transformation. We can see how the perlite and ferrite are transformed into austenite. On the right image, we can notice here in gray the oxidation of the surface. I will show you now how the oxide scale growth model was integrated in our software. The oxide scale is a multiformed iron oxide that forms at high temperature higher than 700 degrees Celsius. It can contain 3 types of oxide. However, in the temperature range that interests us, 850 degrees to 1100 degrees Celsius, we have mostly westite. And even if the balance diagram predicts the presence of other phases, in the literature it has been largely established that we get almost only westite in the industrial conditions. We make the assumption that the oxide is only formed of the westite and that the growth kinetic of westite is due to oxygen diffusion. The oxide scale is function of the surface temperature, the heating time, as well as your material. To validate the gross oxide scale model, the numerical result of oxidation gain weight has been compared with literature data. The simulation results are drawn in black, and the numerical results here we have in blue and different colors. Oxidation kinetic at different temperatures shows that a fast oxidation period is always followed by a slow oxidation period. At the right side, the model has been validated for a long heating time, a heating time around 20 hours. Here we can check that the oxidation kinetic model has a parabolic equation on the fusion mechanisms, and after several hours, it becomes linear. The simulation present a good agreement with data reported from literature. In the video, we see the growth of the oxide scale during cooling. At the right side, here we will do another example. We will see the curves show the effect of the oxide scale thickness on the homogenization of the billet center temperature. It can be observed that due to the thicker oxide scale, the homogeneous temperature is longer. Then more oxide we have, more time we need to homogenize our billet temperature. The oxide scale reduces the emissivity of the oxide material, therefore the heat flow decreases. Then if in your application the billet has an oxide scale on its surface, it is important to consider it to model accurately the heating. Here an industrial example of the heating of a cast part. The objective of this example is to see the effect of the calamine thickness on the time required to achieve 950 degrees Celsius on the central axis. At the right, we see the evolution of three curves. The black curve is realized without considering that we have a calamine thickness, not either a calamine growth. In green, the results obtained by supposing that initially there is no oxide scale on the billet surface and that the oxide scale grows while heating. We can remark that by considering the calamine growth, the homogenization took 5 hours more. In the red, the temperature obtained by considering that the part has initially a calamine thickness of 10 mm. You can notice that the heating time to homogenize the billet central axis increases by 12 hours and a half. Then if in your application you have an oxide scale on the thickness of your part, it is very important to consider it to model the heating accurately. Thanks to the development of the oxide scale growth model, the numerical heat treatment results will be more accurate. We have implemented this model as well as a new emissivity function of the oxide scale thickness. Forming operations will be now more accurate because we will be able to model the spalling of the calamine due to the deformation. We integrate new thermal exchange and friction models that take into account the presence of oxide scale between the part and the dies. Second novelty concerns nitriding. The nitriding is a surface hardening process in which nitrogen atoms are diffused into the surface of ferrous materials and react with the base metal to form a hard, wear-resistant, and fatigue-resistant part. The mechanical properties of the nitride layers are induced by the diffusion of nitrogen and carbon as well as the precipitations. The total concentration corresponds to the sum of element able to diffuse in the matrix with element trapped in the precipitates. In fact, the calculation of the equilibrium with thermocalc or GMAT Pro allows obtaining the percentage of each phase function of the local rate of carbon and nitrogen. The chemical composition computed at each mesh element enables local volume variation computation and hardness estimations. In this industrial example, the part geometry is symmetrical, and the quarter of the tooth has been modeled. This type of computation requires a fine mesh on the specific depth of the surface in order to model accurately the phenomenon occurring within the diffusion layer. The surface mesh size has been refined on this diffusion layer. In the core of the part, no refinement is needed, then a coarse mesh is defined in this area. In our software, it is possible to generate isotropic and anisotropic remeshing. The isotropic mesh present on the left is not enough refined to model accurately the phenomena occurring within the diffusion layer. We don't have enough element in the diffusion layer to model accurately. The second mesh is obtained by defining a mesh box with a mesh size of 0.05 mm on the part surface. The third mesh is obtained by generating an anisotropic mesh on the mesh box. The anisotropic remeshing offers a big advantage comparing to isotropic remeshing. In fact, the same mesh size can be created in a specific direction, but with less nodes. For example, a mesh size of 0.05 mm can be reached for a total node of 2,000 nodes. In comparison, 1.5 million nodes with an isotropic mesh are needed to obtain the same accuracy and the same precision. By analyzing the carbon and nitrogen rate evolution here, we can check that the same result accuracy is obtained with both isotropic and anisotropic mesh. And we can notice that the anisotropic mesh, it took just only 23 minutes to make this computation on 6 cores, and that we need 21 hours to make this computation with isotropic mesh. Here's the evolution of the nitrogen and carbon diffusion during a nitriding process. The nitrogen and the carbon increases in the T diffusion layer. Residual stresses are related to the volumic mass variation due to nitrogen intake at the surface. Von Mises stress magnitude is obtained. Here we can see we have 1000 megapascal on the surface of the part. In the teeth corner, the von Mises stress are around 600 MPa. You can see from the principal stress that the reduced magnitude of the residual stresses at the corner of the teeth is due to the balancing of the compressive stresses near the surface by tensile stresses from the interior. Today, you can model the nitriding process and take advantage of the anisotropic mesh features to speed up your computation time. Next novelty concerns the induction. A key aspect in the design of your production line is the life cycle of the inductors, which will suffer from mechanical and thermal fatigue. Until today, the inductor was considered as a rigid body. By modeling the inductor as deformable, we can predict more efficiently the temperature evolution and the heated affected zone. From the next release, you will be able to do a fully thermomechanical simulation, taking into account thermal dilatation due to Joule heating, as well as distortion due to the Lorentz forces. Thanks to this development, you will better design your inductor by anticipating its deformation. For those who run induction simulations, the computation time may be long, so we have worked on this topic. We made two new developments. The first one is the resolution of the time integration problem using second-order methods for the electromagnetic PDE equation. Thanks to this development, the electromagnetic PDE has a better convergency. The second one is the integration of the mesh L adaptation. This development leads to the reduction of the computation time due to the remeshing. Then thanks to these improvements, the CPU time have been reduced by 15% and by keeping the same results accuracy. Another novelty concerns the quenching and artificial aging of aluminium. Aluminium is a durable, light material that is easy to cast or form. It is only through heat treatment that it obtains the necessary mechanical properties for industrial purposes. Today, you can model the heat treatment of aluminium alloys. The quenching is taken into account through a phenomenological model based on the calculation of a quenching factor QFA. that measures the effectiveness of the quenching. The prediction of this factor is based on the dependency to the amount of untransformed solute during quenching. We can notice a competition between two contradictory mechanisms, the diffusion of chemical elements and the nucleation of precipitates. After performing the quenching, the next operation is aging. Aging is characterized using the Shercliffe-Ashby model, which established that the final mechanical resistance is given by the superposition of three contributions. A minimum contribution corresponding to aluminium in its pure state, a contribution due to the additional compound present in the alloy, and lastly, a contribution given by the precipitates that appear during quenching and aging. It is through the coupling of both models, as illustrated here, that it is possible to fully simulate a consecutive quenching and aging heat treatment of an aluminium alloy. It is thanks to this coupling that Shercliffe-Ashby model gets its interest. This animation presents the evolution of the quenching factor after quenching and artificial aging on a wheel rim. Two new material data files will be available in the next release. One is for aluminium 7010 and the other is for aluminium 7175. A collaboration with Mondragon University is realized to determine the parameter of the aluminium 6082. Now it is time to present you the two case studies. We have been working for several years in collaboration with Quaker and Auton to enrich the quotient database of our software. 63 quotients of Quaker Auton have been added as quotient medium. Today, companies need to think about green solutions, therefore, they need to consider other solutions than oil baths for quenching. The main challenge is that the new quenching fluid must have a similar behavior than the initial one while respecting new constraints. Do we have the same microstructure after quenching? Do we have similar residual stresses and distortion levels? The question is, how do we proceed to choose the best polymer solution and to be sure that we will have similar effects? A first qualitative approach, which doesn't require simulation, is to compare the drasticity curves of the different quotients. In fact, if we manage to replicate the drasticity curve of an oil quotient with a polymer alternative, the industrial product will also follow the same behavior. Let's consider a classical Quaker Houghton oil quotient, the OctoQuench C1804, used by many customers for bearing rings. The drasticity curve of the oil is drawn in yellow. By drawing the polymer AQ300 drasticity curve, you can see here that the polymer has a similar maximum cooling rate as the oil quotient. To go further than the drasticity curve, we compare the heat transfer coefficient. At this point, we cannot be sure that the bearing ring properties will be the same. That's why we will use a numerical simulation to model the quenching of a bearing ring with the different quotients and see the effect on the industrial piece. In this case, we will compare these results to two extreme quotients, a very drastic one, which is the agitated water, and a real slow one, like a slow speed oil, for example, the Quaker Houghton C105. If we look to our initial oil quotient and our polymer candidate, we can see similar behavior in both cases, with quenching time around 70 seconds. We can compare these quenching times with the one of two extreme quotients, the water quenching that take 10 seconds, and oppositely, a slow oil that the quenching time is about 2 minutes. These differences will have an impact on the microstructure. For the agitated water, we have exclusively martensite in the bearing ring, leading to an homogeneous hardness in the same area. However, the high-rate cooling lead to important residual stresses which cause distortion and potential cracks. On the other hand, with a slow oil quenching, we have significant formation of benite up to 20% in the bearing ring, which lead to heterogeneous hardness and unsatisfactory properties. But we have low residual stresses. That's why we target intermediate quenching time. We have to go fast enough to make mainly martensite, but also as slow as possible to reduce to the minimum the residual stress as in oil. The initial oil HQ1804 lead to only 4% of benite, as we see here, and almost homogeneous hardness in the bearing ring. With the polymer candidate, we have identical microstructure, which indicates that this solution may be adapted. We can now compare the residual stresses. We can see that we have identical values for the oil and the polymer solution. Such values are intermediate if we compare with the fast quenching with quenching in water, and by comparing as well, it is intermediate if we compare as well with the slow oil. By comparing only the quenchant characteristic, it is difficult to predict the effect of the quenchant on the industrial product. It is only with the simulation that we made sure that the initial quenching solution could be replaced by the polymer solution. If you want to use a cleaner quenchant solution and guarantee the mechanical properties of your final part, the numerical simulation can be used to help you to know which quenchant to use. Now we will go to another case, to another topic, the induction. Now you will learn about the benefit of modeling the induction heat treatment. Many of you are already familiar with induction hardening. You might be already using it in your production lines or are interested in discovering whether it can be implemented to your processes. Simulation of the induction hardening is a key step to understand and control the key phenomena driving the quality of the final parts. For example, we can predict the evolution of the heated affected zone, the prediction of the metallurgical phase and residual stresses after quenching, understand the energy consumption of the electric generator behind the process. In the following, I will present you a case study made in collaboration with NTN SNR. Then thank you NTN SNR for this collaboration. This simulation is made by two stages, the induction heat treating and followed by a quenching simulation. This treatment is applied on mechanical components in order to create a local structure hardening over a precise depth while still minimizing geometrical distortion and residual stresses. For bearing rings, the objective is to obtain a high hardness on the ball raceway contacts while maintaining sufficient ductility elsewhere. The aim of this case study is to determine the impact of the multiphysical coupling on the temperature, the residual stresses, distortion. Another objective is to determine the set point to be applied to the generator, such as the intensity of the current, the power, and the frequency. The simulation is made on a slice of 45 degrees. Here we see the mesh on which the electromagnetic simulation has been solved. Let's start with the result of the induction heat treating stage. Here we see the Joule heat source term distribution. It can be noticed that it is concentrated near the coil. As well, then we can see that in this zone we have a higher temperature in the near coil. The apparition of the austenite phase. And to the right, we can see the strain distribution. Here are the results after quenching. At the left, the images represent the temperature distribution after induction hardening and after quenching. After quenching, the martensite phase appears near the coil. And in this area, we have a very important hardness. Then we have a hardness of 750 Vickers. At the right side, you can easily analyze the geometrical distortion of the part after quenching. Then by comparing the original shape and the final shape, we can see the distortion of the part after quenching. The comparison between the simulation and experimental measurements shows strong correlation. That's why companies like NTN SNR trust us. The microstructure and phase distribution are in good correlation. Here we see the numerical result. We can notice that the martensite distribution is identical to the one obtained experimentally. To the right, we have the hardness and the residual stresses function of the depth from the surface. In dot dash are the numerical results. The residual curve are plotted in red and the hardness in black. Numerical hardness are in very good agreement with the experimental one. Now we'll go to the conclusions. At the TRANSVALOR, our aim is to simulate the reality as accurately as possible. As we have seen, we have taken now into account the oxide scale or the inductor deformation to provide you more accurate solutions. Today, you can optimize your nitrating heat treatment process with a key features, so anisotropic meshing to reduce your computation time. You can improve the design of the inductor by mastering its deformation. Thanks to the recent improvements related to electromagnetic computation, your result will be more accurate and the CPU time will be reduced. Thanks to our solution, you can follow the evolution of materials property through simulations. Our solutions allow the definition of a complete heat treatment cycle by controlling the different heat treatment operations. It is possible to generate a report of production with numerical results such as temperature evolution, heated affected zone, phase transformation. Our solution integrates an optimization model. SIMHEAT and Forge have the same strong and robust solver. We provide, of course, software licenses, but also engineering services for customer and non-customers. Based on 37 years of experience and software knowledge, we are able to realize for your simulations or even tailor-made developments when you need to quickly reply to a call for a tender or when facing specific manufacturing issues. Even if you think you don't have the needed skills within your company, we have a dedicated team of experts specialized in numerical simulation and material science to help and train your teams. Let's discuss your needs. Now we have reached the end of this webinar. Thank you very much for your attention. If you wish further information about TRANSVALOR and its solution, do not hesitate to contact us.